Now, usually the last lecture of the semester we set aside for doing a series of demonstrations that students have responded favorably to. And I want to make an exception to what I normally say in my lectures. I usually say that everything we talk about will appear on the examination. Well, this lecture is an exception. And so what I'd like you to do is put your notebooks away and sit back and try to follow what we're doing here. Now, we've talked throughout the semester. Throughout the semester, we've talked about a variety of topics. The last one that we talked about is chemical equilibrium. And I'd like to go through a series of colorful demonstrations to show you how the position of equilibrium can be changed by simply changing the concentration or by adding an appropriate solution to another one. And the best thing that you can do perhaps is to see these changes is to look on the monitor, because I'm going to do them in these relatively small beakers here. I'm going to start out with some water in this beaker. I'm going to add to it some solid ferric nitrate. And the color that develops here is the color of the ferric ion, which has some water molecules attached to it. It's the color of the aqueous ferric ion. Now, by changing the concentrations, you can see that the representation of what I've done here is a reaction between solid ferric nitrate, adding water to it to get this ion here, the Fe with H2O taken 5 times and 1 hydroxide in it. And this ion is the ion whose color you see here. Now, by changing the conditions of the reaction, what I've done here, I have a series of beakers that contain a solution of solutions of the aqueous ferric ion. I'm going to add some acid to this. And as I add the acid, another reaction takes place. And what I've done is simply take the complex ion here, add hydrogen ions to it, and simply add a proton to the hydroxide ion to end up with a new ion, which has, in this case, no color. That is, it doesn't exhibit absorption spectra in the visible region. So what I'm going to do is work with this ion, add a variety of substances, and see what kinds of changes take place. The next thing that I want to do is add chloride ion. And this is in the form of sodium chloride. And you'll see that the color, the characteristic color of this ion doesn't differ too much from the original color of the aqueous ferric ion. So the ion whose formula you see on the screen there has the same color as the original color. Now I'm going to add another substance, which is phosphoric acid. And again, we see that the phosphoric acid reacts with the ferric ion in a special way to give us a new ion. And this ion happens to be colorless. Now we're going to take the same solution and add to it still a different substance, which is potassium thiocyanate. And we'll see that the color of the potassium thiocyanate is this deep blood color here. And again, we have an ion that has its own characteristic color. All we're doing really is changing the position of equilibrium between these various ions whose formulas you see and the aqueous ferric ion. And let's do just a couple more here. There we go. I'm adding fluoride ion now in the form of sodium fluoride. Quite a bit of it. I guess maybe I added a little bit too much. I guess I didn't add enough. The fluoride ion then forms a complex with iron, and we get this new ion that has, again, this colorless property. Now, the substance that all of us use sometimes is a common substance. That's ink. And ink is nothing but a mixture of this iron 3, aqueous iron 3 ion with another mixture, another ion that contains iron. And the formula of the major component of ink that has this, the blue ink that is the one that you see here. So we can take this iron 3 complex and change the position of equilibrium by simply adding these various ligands. Now what I'd like to also do, and I should have put my glasses on before, is demonstrate some of the properties of air. You know, air is a mixture of nitrogen, oxygen, mostly nitrogen, oxygen, some carbon dioxide, and a few rare gases. And what I'd like to do for the remainder of the lecture is talk about and demonstrate the properties of air in a variety of ways, as you'll see here. What I have here is a can that is being heated to drive the air out of it. What I'm going to do, let's just let it heat for a second, is demonstrate Boyle's law to you in a slightly different form than the one that we've talked about before. There's a little water in there. We're evaporating the water to drive off the air. Pretty much the same kind of experiment that you did in the lab when you determined the gram molecular weight of a volatile liquid. Well, as the air is driven off, what I'm going to do now is stopper it and then try to cool it by putting it into this ice mixture here, ice-water mixture, and see what happens to it. This has got to be a little bit tight, and we'll just let that go for a while. All right. Hello. And what you see is happening is that the can is, see in here I guess, is making a lot of noises. The can is collapsing because the pressure outside is greater than the pressure inside. And this is another example of the pressure relationships that we've talked about. It's a little bit hot. You know, this illustrates Boyle's law in a slightly different fashion than the one we've talked about before. You know, this illustrates that the greater the pressure, the greater the volume of hot air. And as this hot air cools down, maybe this will help it along. Well, we'll just let that go for a while now and see what happens to it. Oh, it's happening. All right, that's good. Good. Okay. Well, the two major components of air are oxygen and nitrogen. 20% of air is oxygen, and about 79% is nitrogen. And I'd like to sort of have you keep in mind that the boiling point of oxygen is minus 183 degrees centigrade, and the boiling point of nitrogen is minus 196 degrees C. And so what we're going to do is really talk about the properties of gaseous oxygen, gaseous nitrogen, and also about the properties of liquid air and the properties of liquid nitrogen and liquid oxygen. The other component of semi-major component of air is carbon dioxide. And carbon dioxide has a lot of properties that we've examined, but it has one other property that I'd like to demonstrate to you. That is the reaction between carbon dioxide and calcium hydroxide. And if you look up on the chart, you'll see that I have a reaction there represented by two equations. And what I'm going to do is try to have this solution of calcium hydroxide react with some carbon dioxide. And to do this, I'm going to have to get two volunteers from the audience here to supply me with the carbon dioxide. And So I guess I'm going to call on you. Could you stand up here so everybody can see? And if you just look at that camera over there and and blow into it. Okay, just look over there, okay? And I'm going to try to ask you to come over here. And we're going to have wait a minute. We're going to have a contest to see who's going to give us the most calcium carbonate. So you look at that camera up there. And when I say go, you start blowing, okay? Ready? Go. Don't forget to blow. Make sure you don't suck this stuff in there, okay? Now, what I'm going to do as we're having this little race, see, the more you laugh, the more chances you have of losing. So what I'm going to do is have my own supply of carbon dioxide, and I'm going to, one of the solutions is getting to be cloudy, and so is the other one. And what I'm going to do, I'm going to beat both of you by taking this, no, you just look at the camera, by dropping a chunk of dry ice in there, and pretty soon, fairly soon in fact, you see I have a cloudy situation developing here, fairly cloudy, and point is that their lungs do not supply as much carbon dioxide as can be supplied by means of the chunk of dry ice. How are we doing? Oh, that's pretty good. Thank you very much. Thank you. I'd call it a draw, wouldn't you? Okay. Thank you. Now what I'd like you to do is to watch this setup here and look clearly to what's happening to the solution. The calcium carbonate, which is the insoluble substance, is becoming soluble. In fact, if I help this along a little bit by adding another chunk of dry ice, which is a source of carbon dioxide, you see that we have a means of dissolving the limestone. And the reaction that we're talking about is the one represented on the chart there, but the reaction between calcium carbonate, carbon dioxide, and the water, which forms a soluble salt, calcium bicarbonate. So again, this is an example of how you can shift the position of equilibrium by simply controlling the reaction conditions. Now, it would have taken them about 2 hours to supply enough carbon dioxide to get all the calcium carbonate to dissolve, and I think they have better things to do. Okay, now, in looking at the other components of air, where we've looked at carbon dioxide, we're going to look at liquid nitrogen and liquid oxygen, and again, we're going to look at helium, which is a very, very rare gas and is present in small amounts in the atmosphere. And so, in talking about liquid nitrogen, we're talking about liquefying air and getting the nitrogen and oxygen separated from each other, and this can be done by a variety of means. One, by taking advantage, for example, of the differences in the boiling point. We can liquefy air and take advantage of that and have some liquid nitrogen. And let's see if we have some liquid nitrogen here. I'd like to show how's the can doing here. Can doesn't look too good. And so what I'd like to do is get this can out of the way. Just set it over here. That's so funny. Oh, you're watching yourself. I see. It's a funny experience. I know it. See, my lab technique isn't so good. Okay. Okay, well, we were going to go from one liquid to another, and we're going to go from liquid water, nice, to some liquid nitrogen. And here's some liquid nitrogen. You see, it's a very good liquid that can be used very efficiently for removing dust, because because once it collects the dust in one area, then it evaporates and is converted to the gaseous state, and we don't have to worry about it, and somebody has to go and pick up the dust. It's getting a little bit wet here. Oh, all my notes are... Okay, so what we're going to do now is show you that we can use liquid nitrogen for a variety of purposes. One of them is to cook in it. And I'm going to put some liquid nitrogen in the coffee can. I'm running out of liquid nitrogen here, so let's get a little more. And since liquid nitrogen is at a very low temperature, in fact, its boiling point is minus 196 degrees, I'm going to heat up the liquid nitrogen by means of this ice-water mixture. And let's see if that will work. We'll get to see, it's boiling already. And you can see that you can see that the cold ice-water mixture is supplying heat to the much colder liquid nitrogen. That's a very different way for us to think about boiling, but that's what's happening. The heat coming from the ice is causing the liquid nitrogen to boil. So in terms of readjusting our temperature scales and our way of thinking about heat and absence of heat, you can see that it requires a change in it. So I'm going to save this liquid nitrogen because I want to use it for a different purpose. Oops. Okay, so what we can do, it won't do anything to you. It's just very cold. You see, you can just pour it on your hand like this and make sure you don't cup your hand because then you'll get a burn, which is what I just did. So, okay, so one of the questions is, okay, if it's so cold, how do we keep it? Where do we keep it? Well, we keep it in these thermos bottles. They're insulated, and except that scientists have a fancy name for these thermos bottles. They call them Dewar flasks. And so we're going to be keeping the liquid nitrogen in the Dewar flask and working with it. And it's really pretty wet down here. Okay, well, let me just do something else here. Let's go back to our liquid nitrogen here. Let's just add a little more. And now, instead of supplying heat from this ice mixture, let's just really heat the hell out of it and really get it to boil. You see it's boiling all over the place, but you also see that something else is happening to it in terms of it's turning color. And let's just see what's happening here. Can't make up my mind whether it's too hot or too cold. Okay, if you look at the bottom of this, you'll see some white material there, and I want to see if you can figure out what this material is. Does anyone have any ideas? Huh? What? Somebody says it's CO2 or water. Well, water. Where did the water come from? From the frozen air. Frozen air is on the inside. What's that? That's right. We're burning methane, natural gas here, and the product of the combustion reaction are CO2 and H2O. And so we're getting a mixture of frozen moisture here and some solid carbon dioxide or dry ice. And in fact, this is a good way of making carbon dioxide. It's not a very good way because you have to use liquid nitrogen, which is much more expensive than carbon dioxide. So we'll just let that go for a while and move on to talk about the properties of other substances in liquid nitrogen. And one of the substances we want to talk about is natural gas. And what I have here is a Dewar flask containing some come prepared, right. What I have here is this liquid hello. Let's cool it off again. I guess I warmed it up too much. What I have is a liquid form of methane. Now, the boiling point of methane, CH4, has a boiling point of minus 126 degrees. And you see it's a higher boiling point than liquid nitrogen. So we can then liquefy gaseous methane and have it in the liquid form. And who did it? I guess I did it. It's still in there. What? It's off again. Oh, I see the glass stuck to it. Yeah, it's still in there. What I'm looking for is another, oh, here we are, another door flask. Wonderful. Again, wonderful. I keep telling you my technique is sloppy, but okay, let's see what happens now if we put it over here. Well, I already saw what happened there. And the freezing point of methane is below minus 196. That's why it doesn't freeze. So now we can get this out of the way and see what happens with our methane. And what we're going to do is try to use this methane as a source of fuel. And let's see what happens. We've already had one disaster. And what I have, you see up on top here, is a nozzle out of which the methane is going to be coming out in the gaseous form. We already know what the properties of methane are. Now, the thing to remember here is that we have a very high concentration of methane. There we go. See the flame? You see the flame? It's coming out so fast that it's putting out the flame. Freeze a little bit. Cool it, in other words. Okay, let's try it again. Hello. You see it? Just dump it out. And I guess we're lucky we didn't have a fire, because with that, all that concentration of methane down there, we could have had a slight problem. Okay, well, what I also want to do now is look at another fuel, which is kerosene, and I'm going to make. You think I'm crazy, don't you? Okay, I'm going to put some kerosene in here. Okay, and then I'm going to let it sit in this liquid nitrogen dewar for a while. And I'm also going to take a little bit of everybody's favorite compound, which is ethyl alcohol. And you know, ethyl alcohol has a lot of uses. It's used as antifreeze. I see I don't have to tell you what else it's used for. Okay. I'll get rid of some of these things here. And, oh, what did I do with the ethyl alcohol? I didn't put it anyplace. Thank you. Okay, let's get a little more nitrogen here. I don't have very good aim, do I? Okay, and just let this freeze in here for a while. Actually, we have a little too much in there. Well, we'll let those go for a while and see what happens. So we'll come back to them in a little while and see what happens to them. Now, I'm going to look at some other substances that I have here. I have this rubber ball, and just to verify that it is a rubber ball, why don't you? I don't think we want to sign it. We can't catch it. See that? Watch this. Watch this. We got a basket. Okay, so what we're going to do is take this rubber ball, and we have another rubber ball here too, and we're going to add a little liquid nitrogen to it and see what happens. And we're also going to take these small pieces of rubber that you see here, and we're going to freeze those too by, whoops, I keep forgetting. Just give it a little more. It's kind of thirsty there. And see what happens. Get in there. There we go. I can't get it out. Oops. Okay, well, see if we can get it. There we go. You see, it still looks the same, except that its properties are quite different now. You see, and it. What we've had there really is a shattering experience, you know. Okay, let's see what's happening to these other guys down here. Where did I put my? There they are. The hell with them. I'll just get them out. See, they're pretty hard too. And what I'm going to try to do now is use this hammer to drive the nails, which I have just made, these rubber nails. There we go. We have these rubber nails. Drive them in here by means of this mercury hammer. What I've done here is freeze some mercury in this form. Let's see how well it works. I hope nobody reports me because I don't belong to a union. Whoops. Let's see what happens now. And we'll just let them sit, see what happens to them a little later. Okay. Well, let's see how we're doing with these, with the alcohol. I knew we had a little bit too much here, but let's add some more to it. And let's see what's happening to this over here. Well, you can see that the kerosene is freezing here, and it's almost frozen. What I'm going to try to do is to get this out. There it is. And what I have here is no wisecracks now. Where are we? What I have here is a kerosene candle. Let's see how that's going to work. Stand by. I have a pretty long wick on it. That was a mistake, I guess. But this lecture is full of mistakes anyway. Come on. What's that? It was planned. No, no. It's a result of not planning. Okay, well, we'll just let the kerosene candle go for a while and see what's... Well, still going. Okay, we'll just let it go. And get back over here and see what's happening to our ethyl alcohol. And you see that what has happened to it, it has become frozen. What we really have is a situation where we have some hard liquor now. Ooh. Okay. Well, what I'd like to do now is, actually it's getting a little too hot here. What I'd like to do is, it's a little too warm, so I'm going to take this off and I think that's well, I'm glad you agree. Okay, let's see what happens to this balloon here when we add some liquid nitrogen to it. A little more. I can't find any more. There's more. Who wants it? Just leave it. Let's let it sit there. Okay. And you see the... now I... That's a $25 balloon. Mr. Hirsch would like to get it back. Now, as some of you know, in fact, at least one person in this course knows that I taught at the University of Illinois because his brother took my course there. And he tells me that the lectures are a little bit better, but the jokes get worse every year. And so, in order to salute Illinois, I'd like to ask Vince and Tally to come out and do a little rendition for us here.
Hail to the orange, hail to the blue.
Oh, Bucky. Bucky, I really appreciate your coming out here with that. What's that thing that you're holding? Can I handle it? What do you do with it? Play lacrosse with it? Bucky, what I'd like to do to make up for singing Hail to the Orange, Hail to the Blue is have a few demonstrations just to try to make you happy and to prove to you that my allegiance now is to Wisconsin, okay? You let me do that? That dumb animal. Okay, what we're going to do now is have a salute to Wisconsin. So Vince and Talia will also come out and try to redeem themselves. Since you guys did the singing. You watch carefully, Bucky, now. Bucky? No, it'll go. Okay. No singing this time?
On Wisconsin, on Wisconsin, friends right through that line. Round the bar, touchdown, sure this time. You,
What is happening here? Is anything supposed to happen?
Oh.
There you go, Bucky. How about that? Well, Bucky, I'm going to do something that you're used to, using a gas that is very rare in the atmosphere. That's helium. And you just watch this, Bucky, see if you like it, okay?
Good evening, hockey fans.
How's that, Bucky? Is that good? Okay. I guess I got a pretty heavy dose of that. Let's see what we're going to do next here. Okay, well, what I'd like to do, Bucky, is dedicate this poem that was written to you and see if it meets with your approval. This poem was written by a variety of people that contributed significantly to it, and I'd like to share it with you. Goes something like this. There once was a girl from Nantucket. No? Don't like that? Okay, I'll try another one, Bucky, okay? I'll try to keep it decent. Goes something like this. Once upon a Christmas dreary, in the lab of Shakhashiri. Christmas, you say, and in the lab? Oh, it's okay. It's better than driving a cab. Do I have to explain that to you? Ring stands stood in darker gloom, scattered widely around the room, so thin and spare that none could match the cedars of Lebanon. I have to explain that to you? I was born in Lebanon. No mistletoe there was for kissing. Even you, the stars, were missing. I didn't write this. You'll get to the part that I wrote, so I'll get to it. Once suddenly there was a knock. Cheery stood in a state of shock. I didn't write this one either. Out from the hood jumped Santa Claus, holding 103 books in his paws. Your lecturer enjoyed the glow of the complete combustion of Drago. I wrote that one. Santa started to do some flips when he heard about chem tips. Then he shrieked, "From my helper keep abreast. She's not taking your hourly test. Keep your hands off my sweet blonde. I know about your covalent bond." He was being completely unfair. As a Lewis acid, all I wanted was a pair. Santa, while he could, started leaving through the hood. He disappeared with fanfare and Shakhashiri standing there, so an endpoint in the air. How's that, Bucky? Well, Bucky? Bucky, I'd like to do one more thing for you before you leave. And what I'd like to do is, in front of you, show my appreciation to the person who really got me some hockey tickets this year. And but before we do that, I want to see the effect of the liquid nitrogen on this rose. And you see, nothing really happens to it. It just gets colder and rises to the top, and we have this rose here. And so I'd like to ask Chris, if you'd come out here, please. I'd like to present you with this as a token of appreciation for getting me the hockey tickets. Actually, you've been a good sport. Here's a nice, real one for you. Is that you I smell, Bucky? Bucky, you've been a good sport also. Here's one for you. Thank you very much for coming, and Merry Christmas. Thanks, Bucky. Okay, what I want to do now also is continue with this series of demonstrations and look at the effect of liquid nitrogen on life. We've seen the effect of liquid nitrogen on a flower, and what I want to do now is get some more liquid nitrogen. Here we go. And put some liquid nitrogen in the beaker and try to cook some breakfast. What I'm going to do is cook a 3-minute egg here by cooking it in liquid nitrogen. Let's see what happens to it as we go through the cooking. I'm also going to take some grapes and cook those. We'll put them in there and see what happens to food when we go down to low temperatures. I keep running out of this stuff. You see the liquid nitrogen is boiling there. The egg is cooking away, and we'll see what happens to it. We'll add a little more here, and we're running out of liquid here, so let's add a little more there and see what's happening. Now, as the egg is boiling away, let me just put a little more liquid nitrogen here. I keep running out of this stuff. Watch this. Now let's see what happened to our, whoops, they're really frozen. Here what I'm going to do is throw them out to you and ask you not to eat them. Oh! We'll try my left. There we go, and you can pass them around. Don't hold them too long. There we go. Because they do give you a frostbite eventually. And let's see what's happening to our 3-minute egg here. Oops. There it is. Now what we have is a cooked egg. There you go. Whoops. It's not really well cooked. In fact, it's probably similar to the eggs you get in the dorm. You know what? To see the effect of liquid nitrogen on life, I went this morning to the city pond and picked up a little animal, which I'd like to bring out right now. Come on, little fella. Come on, come on. Come on, come on. Come on. Come on. And here he is. Our little fella here. And we're going to put him in the liquid nitrogen and cook him. And we're going to see what happens to him as we do this cooking. This is a 19-cent ball. Wow. I think I'll keep it. And he's boiling away there. See what happens. How are you coming along? It's really coming along nicely. See how he's doing. Doggone. Really. Louder, louder. Okay, now, we're really coming to the end here, and I would have liked to demonstrate to you the properties of liquid oxygen, but we see we're running out of time. And I do want to acknowledge the help of all the teaching assistants that helped me this semester, and hopefully will help me next semester. I also want to acknowledge the help of the television people in making this possible. And I especially want to thank Tally and Vince for the help that they did. And I'd like to get Tally to come out here, and because this is a special occasion, before we go on to Christmas break,
Pardon me?
I would like to get Tally here to do a little demonstration completely on his own. If he screws it up, it's his fault. If it turns out fine, then he should get the credit for it. So Tally?
This one?
This one. You want to tell us what you're doing? Yeah.
I just want to demonstrate some colors of in the Christmas spirit. So I have acid and base in these different beakers, and I'm going to add some indicators to acid, base. That's methyl orange. Here's methylene blue. No, this is bromethymol blue.
Who cares?
Acid and base. And here's litmus. Acid and base, I hope. Base and acid. Here's phenolphthalein. Nothing in acid. Beautiful in base. But after you've got it done, further in the Christmas spirit,
Well, thank you very much for coming. Good luck on your finals, and have nice holidays. You gotta come to the...